Hello, welcome to another module in this massive open online course. So, we are looking at example problems, various example problems to better understand Fourier analysis. So, let us continue our discussion. So, we want to look at example problems. To better understand the concept of Fourier analysis. In particular, we have started looking at the Fourier analysis representation of this periodic square wave, correct. If you remember, you might remember we have started looking at the Fourier analysis of this periodic square wave, which has a time period, fundamental period, that is of t naught, each pulse is of width t naught over 2 and height 1. Okay. The period, fundamental period of the signal is t naught. We have looked at the CEFS, the complex exponential Fourier series. We want to look at the TFS, that is the trigonometric Fourier series of this signal, that is the periodic square wave. Okay. And the TFS can be obtained as follows. To obtain the TFS, so we are continuing the discussion. So, the TFS of the above signal can be obtained as follows. Remember, the TFS of any signal xt is given as, so we have the TFS is given as xt equals a naught over 2 plus summation k equals 1 to infinity a k cosine k omega naught t plus summation k equals 1 to infinity b k sine k omega naught b k sine k omega naught t. And now we know also the relation for these various a k's. For instance, a naught, we know a naught by 2 equals c naught from the properties of the TFS, which implies a naught equals twice c naught, and we have already evaluated c naught. C naught you can see is half. So, a naught is twice c naught, which is twice into half equals 1. So, we have a naught equals 1. Further, we have the coefficient of cosine omega k omega naught t given as a k equals, we know, c k plus c minus k. Now, we know c k's are 0 if k is odd, or c k equals 0 for k even k, implies now a k, which is c k plus c minus k, is also therefore 0 if k is even, because both c k and c minus k are 0 for even k. Okay. So, implies a k equals 0 if k equals even, since both c k and c minus k are 0, and if k is odd, let us say k equals 2m plus 1. Remember, for odd k, the expression of c k is c of 2m plus 1. We have, for odd k, we have c of 2m plus 1, and we have derived the expression for this, that is equal to 1 over j pi 2m plus 1. So, c of 2m plus 1 equals 1 over j pi 2m plus 1, which implies basically that your a k equals, or a of 2m plus 1, since k equals 2m plus 1, a of 2m plus 1 equals c of 2m plus 1 plus C of minus k, that is C of minus 2m plus 1, which is 1 over j pi 2m plus 1 plus 1 over j pi minus 2m minus 1, minus of 2m plus 1, that is minus 2m minus 1, and you can clearly see these two cancel each other. So, this is 0. So, basically what we have been able to show that A k is 0 if k equals k is even, and A k is 0 A k is 0 when k is odd as well, which implies A k is 0 for all k. Okay. So, this basically implies, so A k is 0 for k either even or odd, which implies A k equals 0 for all k. Okay. So, the coefficient of cosine k omega naught t is 0 for all k. Okay. Now, let us then look at what is b k. Now, b k is basically, you can see, we know the relation for b k, that is j times c k minus c of minus k, which is once again equal to 0 if k equals even, because remember again, if k is even, c k is 0, c minus k is 0. So, b k is also 0. If k is odd, then b k can be simplified as, let us assume k equals some odd quantity 2m plus 1, then b k equals j times c k, that is 1 over, if I remember correctly, that is 1 over j pi 2m plus 1 minus 1 over c minus k minus 1 over j pi minus 2m minus 1, which is equal to twice, the j's cancel. So, this is equal to twice pi over 2m plus 1. Okay. So, b k equals, or this is in fact b of 2m plus 1 when k is odd. So, b of 2m plus 1, b of 2m plus 1 is given by this expression, and therefore, finally, x of t, the TFS is given as follows. We have x of t equals a naught by 2, a naught is 1. So, this is half plus b k summation b k, but b k is non-zero only for e odd k. So, this is basically summation m equals 0 to infinity 1 over or 2 over pi 2m plus 1 times sine of 2m plus 1 omega naught t, and if you take the 2 over pi common in the summation, what you have is you have x t equals, you have x t equals half plus 2 over pi summation m equals 0 to infinity 1 over 2m plus 1, in fact 1 over 2m plus 1 sine of 2m plus 1 times omega naught t, and this is the trigonometric Fourier series. This is the TFS. Of the this is the TFS of the trigonometric Fourier series of the TFS, that is the TFS of the periodic square wave, and you can further simplify it. Just to illustrate it, you can write it as half 2 over pi for m equals 0, this is simply sine of omega naught. For m equals 1, this is 1 over 2m plus 1, that is 1 over 3 sine of 3 omega naught t plus 1 over 5 sine of phi omega naught t plus so on and so forth. So, this is the again this is your TFS, that is the trigonometric Fourier series representation. So, we have looked at the example problem in which we have considered a periodic square wave of pulse width T naught over 2, fundamental period T naught, height 1, and we have derived the both the CEFS as well as the TFS representations for this periodic continuous time periodic signal. Okay. All right. So, let us proceed to the next problem, which is the following thing. Let us consider now a periodic impulse train, and this has a lot of relevance in sampling, which we will see later. So, this is problem number 3. It is the periodic impulse train, which is basically a train of, this is nothing but a train of impulses so at this train of successive impulses with successive impulses at a spacing of t naught. So, you have impulses at 0, t naught, twice t naught, thrice t naught, minus t naught, minus 2 t naught. So, impulses are integer multiples of t naught. So, the spacing between impulses, successive impulses is t naught. So, you can say this is a periodic signal. Okay. So, this is an impulse train, this periodic signal comprising of impulses unit scaled impulses spaced at periodic intervals of t naught, right, at multiples of t naught is termed as an impulse train. Okay. So, this is a periodic signal, or you can call it as a periodic impulse train. Okay. So, this is an impulse train, or this is in fact a periodic impulse train, an impulse train that is periodic, and we want to determine for this we want to determine the what we want to determine is once again we want to determine the CEFS and as well as the TFS for this periodic impulse train, and this is fairly simple. So, let us call this as delta T naught of t, this periodic impulse train with spacing T naught. You can see this is nothing but summation k equals minus infinity to infinity delta impulses at every integer multiple of t naught. Okay. So, this basically denotes an impulse at multiple impulses at integer multiples of t naught. Okay. Now, if you look at any particular period in minus t naught over 2, for instance, in minus t naught over 2 to t naught over 2, this is simply delta t in t less than minus t naught over 2 less than equal to t less than t naught over 2. So, this is simply the delta t if you look at one contiguous interval of duration t naught. Okay. And therefore, the coefficient of the Fourier series, remember, that is Ck is given as Ck can be evaluated as follows. So, we have Ck equals 1 over t naught integral minus T naught over 2 to T naught over 2. It is particularly convenient to choose minus T naught over 2 to T naught over 2 because the impulse is contained, well contained in this interval. So, that is x of t e raised to minus j 2 pi k omega naught t, which is basically in this interval, this is simply the delta function delta t e raised to minus j 2 pi k omega naught t dt, and by the property of the delta function, this is simply the value of the function, that is e raised to minus j 2 pi k omega naught t evaluated at t equal to 0, and this is simply 1 over t naught, since e raised to minus j 2 pi k omega naught t evaluated at t equal to 0 is 1. So, each of the Fourier series coefficients, the coefficients of the complex exponential Fourier series, that is the coefficients of the CEFS, all the coefficients are 1 over T naught. So, each Ck is 1 over T naught. Okay. So, you can see that each Ck is basically 1 over T naught, and therefore, the complex, the CEFS is given as, that is your delta T naught t equals 1 over T naught summation k equals minus infinity to infinity e raised to j k omega naught t. And the trigonometric Fourier series, the TFS of this can be obtained as follows. The TFS is given in a straightforward fashion. Remember, delta T naught of t, I can write this as summation as a naught over 2 plus summation k equals 1 to infinity a k cosine k omega naught t plus summation k equals 1 to infinity b k sin k omega naught t. Now, a naught equals a naught by 2 equals C naught, which is basically, remember, C naught is k equal to 0, that is 1 over T naught, because all Ck are 1 over T naught, which implies a naught equals 2 over. So, this implies that a naught equals 2 over T naught. Further, a k, remember, a k is Ck plus C minus k, both Ck and C minus k are T naught. So, a k for any k is 1 over T naught plus 1 over T naught, that is twice T naught. Okay. So, this is Ck plus C minus k, that is twice T naught 2 over T naught, and Bk equals j Ck minus C minus k, which by the same logic is 1 over T naught minus 1 over T naught equals 0, that is j times Ck minus C minus k. So, x t, now putting it all together, the TFS is x t equals a naught by 2, that is twice over T naught by 2, that is 1 over T naught plus summation k equals 1 to infinity a k, that is twice over T naught. So, twice over T naught is common to all. So, I bring it out of the summation. So, this is twice 2 over T naught summation cosine k omega naught t. This is the TFS of the impulse tree. this is the TFS of the impulse train, that is a trigonometric Fourier series of the impulse train, which is 1 over T naught plus twice over T naught summation k equal to 1 to infinity cosine k omega naught t. Okay. So, basically that explains the trigonometric, both the CFS and the TFS of the impulse train, and as already alluded to, this plays a very important role in the sampling of a continuous time signal, and which we are going to look at slightly later in one of the later modules. Okay. Let us move on to another problem. Let us now look problem number 4. Let us now look at a triangle. So, we have considered various periodic signals, we have considered a square wave, we have considered an impulse train. Let us now consider a triangular wave, which is slightly more difficult to analyze. So, here I have a periodic triangular wave of period T naught. So, this is 0, T naught over 2, T naught, 3 T naught over 2, twice T naught, and so on, minus T naught over 2, minus T naught. Okay. And what I can see here, and let the height of this be equal to T naught over 4, just choose something convenient as. So, this is height equals T naught over 4, and this is your periodic triangular wave. Okay. We have seen a periodic square wave before, this is a periodic triangular wave. This is a periodic triangular wave, and what we want to do again, once again, for this signal is we want to determine the CFS and the TFS for this. Okay, this periodic triangular wave. Of course, one can employ the straightforward approach here, that is write down the CFS and derive the expression for each coefficient Ck, but we are going to use a nice trick here. First, what we are going to do is we are going to differentiate this, and once you differentiate it, you will see that we will get something very interesting. Now, if you look at this triangular wave, now the slope in the rising part of this is the height of this triangle divided by the width. So, the slope of this, if you look at the slope of this, let us call this signal xt. Okay. So, periodic triangular wave xt. So, the slope of this, interestingly, is the height T naught over 4 divided by the width of the rising part, that is T naught over 2, which is basically equals half. So, the slope of this is half. So, the slope of the rising part is half, slope of the falling part is naturally this symmetric. So, this slope is minus half. So, what we have is, if you differentiate it, that is if you consider x prime t. So, consider x prime t equals dxt over dt, that is a derivative of xt. Now, x prime t, if you can draw it, x prime t will look something like this, that is at time 0 it starts at half, because the increasing slope is half. So, it is half for T naught by 2, and then it is minus half for T naught by 2, half, minus half, and then it keeps continuing. Okay. So, and so if you call this height as half, so this is T naught by 2, this is T naught, 3 T naught by 2, this is twice T naught minus T naught by 2, this is minus T naught. Okay. So, this you can see, let me just write this a little clearly. So, this is T naught by 2, this is T naught and so on. So, we get periodic square wave. In fact, this is basically oscillate, this basically goes has a height peak of half and a negative peak of minus half. Okay. So, this is basically this point is minus half. So, this is your x prime t. You can see this is very close to the periodic square wave that we have seen before. So, this is your x prime t. Now, let us consider x tilde t which is x prime t which is x prime t plus half. So, shift this basically on the y axis by half. So, push it up, add half, x prime t equals half plus x t. If you consider x prime t equals half plus x t, you will observe something interesting. What you get is you will get a periodic square wave now of height that is half of height that is 1, and this is something that we have seen before. So, this is 1, this is T naught by 2, T naught, 3 T naught by 2 twice T naught, this is 0, minus T naught by 2 minus T naught and so on, and this is basically your periodic square wave that we have seen before. Periodic square that we have seen before, and this is basically your this is what we are calling as this x tilde t. This is what we are calling as this quantity x tilde t. So, what we have shown is that the periodic square wave that we have derived before is x tilde t equals x prime t plus half, which implies that x prime t, that is dx by dt, x prime t equals x tilde t minus half. Okay. So, here x tilde t, x prime t equals x tilde t minus half. All right. So, we basically started with this triangular wave using the differentiation, considering the derivative, we have reduced it to the periodic square wave, something that we have seen earlier, and we will use this property now to derive both the CFS as well as the TFS of the periodic square, periodic triangular wave. All right. So, let us stop here and continue with this problem in the next module. Thank you very much.